welcome to another edition of the NPTEL online course on Microelectronics, devices and circuits. What we will do today is look into the basic feedback topology. If you remember, in our previous module, we had discussed about the concept of negative feedback. What is the meaning of negative feedback? We have seen that in order to have a negative feedback, the general scheme is basically with the amplification with feedback is equals to amplification without feedback upon 1 plus A beta, where A beta was referred to as the loop gain, right. And as long as A beta is greater than 1, right, you will automatically have AF less than A, and we refer to this as a negative feedback. That means, with feedback the gain is reduced. Similarly, if A into beta is less than 1, then you get your AF greater than A, because the denominator actually becomes less than 1, and this is referred to as a positive feedback, right. So, in most of the cases which we will be encountering, we will be concentrating on negative feedback per se, right. And we have also seen that with this loop gain, 1 plus loop gain, if you see, and that is known as the feedback factor. So, this 1 plus A beta is referred to as a feedback factor, right. And if you look at the feedback factor, higher the value, lower is your AF, and therefore, in most practical cases we try to keep this one as high as possible. But the advantage of all these things is that your gain desensitization takes place. So, DAF by AF is reduced drastically as compared to DA by A. So, this is gain without feedback, this is relative gain with respect to feedback, right. So, your gain becomes more stabilized. What you lose is basically the gain. So, gain falls down, but your gain becomes much more stabilized with respect to variation in temperature and output electrical characteristics. Similarly, your noise also is reduced, and your signal to noise ratios becomes larger, provided you are able to have a pre-amplifier which is less noisy in series to the noisy amplifier, right. If you do not do that, then it is not possible, otherwise we generally have a lower SNR. The third thing which is, so this is the second part, the third part is basically your bandwidth increases, right. So, bandwidth increases because your lower cutoff frequency goes smaller, and the higher cutoff frequency goes higher, and therefore, the bandwidth increases, but your gain bandwidth product, which is basically GBW, is constant, and therefore, what happens to the gain is that the gain starts to fall down. So, your bandwidth increases, gain falls down, more stability, less of noise, and and there will be nonlinear distortion will be also reduced, right. And these are the very important points of negative feedback. Today what we will be looking into is we will be looking into the various topologies of feedback amplifier. And if you remember in our previous talk, in our previous discussion, the general scheme of things was with the signal flow diagram, if you look, was you had A and then you had beta here. So, beta was basically my feedback factor, and then you have a source of voltage source or a current source here, which was feeding to the amplifier. Then you have a load here, right, and this load was talking to my beta here, and a part of beta was fed into this amplifier, and as a result you will have a feedback factor. So, this was basically your signal flow diagram, if you remember from my previous discussion. Now depending on how you manage this side and this side, this is known as sampling portion, and this is known as a mixer portion. So, depending how you sample and mix, you can have 4 types of configurations available to me. Whenever you sample in a parallel form, you are actually sampling out voltages, and whenever you are sampling in series, you are, so this is basically voltage, this is also voltage, right, because this is parallel, this is parallel. So, parallel basically means that your voltage feedback network is there. Similarly, if you have series extraction, then you have current extraction taking place. So, we have got 2 notations, current and voltage, right. So, current voltage is shunt because it is parallel, and this is basically your series, right. And then you also have you have 2 voltage and current as the 2 part, and you have therefore 2 mixer and samplers. So, in effective we have 4 configurations available to me, right, and these 4 configurations are written here. One is a voltage amplifier, another is a current amplifier, you will have transconductance amplifier and trans resistance amplifier, and then we will recapitulate the whole discussion once again, right. So, we start with voltage amplifier and then we go to current amplifier, transconductance amplifier, and so on and so forth. Now, if you go to the voltage amplifier, right, let us discuss the voltage amplifier first. So, voltage amplifier's main job is to amplify a voltage, as the name suggests. So, you will amplify an input voltage which is very small in dimensions, peak to peak, and will provide an output voltage signal. So, at this stage we are not talking about at this stage at least we are not talking about frequency change, or for that matter the change in the frequency of the inputs source, so on and so forth. We are keeping the input stable at say omega, and we are trying to find out the variation in the peak to peak signal of the output with respect to A and beta. A is the feed forward amplification factor and beta is the feedback network exponent. So, therefore, a voltage amplifier is actually a voltage controlled voltage source. I suppose you can understand this why, because if you look very carefully, you are actually extracting voltage from the sampler and you are feeding voltage into the mixer. So, both are shunt configuration, or both are basically parallel configuration. Now, why it is known as a VCCS or voltage controlled voltage source? The reason is that you are this is basically voltage amplifier. So, the output is basically a voltage which you are getting, right. So, therefore, it is a output is a voltage source. So, and that is the reason you say it to be a voltage source. Why is it voltage controlled? Because the amplifier which you will be using typically here will be controlled by a voltage, right, and therefore, this is basically a voltage controlled voltage source. In this case, as we will see, the input resistance is quite high and the output resistance is quite low, right, just like an op amp. So, op amp is an example of a voltage amplifier, we already know that, and therefore, if you look at op amp, its input resistance is infinitely large or very large and output resistance is very small. Same thing happens to a voltage amplifier here. What we will be looking into is that the output quantity of the interest is the output voltage. So, we will be looking at the output voltage, and since the signal source is essentially a voltage source, it is always advisable that you use Thevenin equivalent, right. So, what we will do is that we will use a Thevenin equivalent when we do a voltage amplifier action or a voltage amplifier division. So, this is the basic architecture of your voltage amplifier here, our basic amplifier. So, as you can see, this is your sampler, right, and this is your mixer here, right. You do have this is the load, and what you do is that this feedback network tries to take a portion of this V0, and therefore, you will have output beta times V0 coming at this point. So, this will be beta times V0 which will be coming here. Then you will have a feedback network, and therefore, you will have Vs minus beta times V0 will be coming at this basic network here. And then what you get from here, or what you get from this basic configuration is that in this case also you will have AF, the feedback width will be equals to A upon 1 plus A beta, right, and that is what happens to a larger extent, right. Now, if you go ahead and do it, for example, I will give you an example. For example, the actual voltage gain series network which you will see is, if you see here, this is basically an example of a voltage amplifier. This circuit here, this R1 and R2 is basically your beta, right. So, beta is basically the parallel combination of R1 and R2 which you see here, and therefore, if you are taking out the voltage out of this particular form, I get beta to be equals to R1 upon R1 plus R2, right, and as a result beta will be always less than 1. So, when beta is equals to 1, it primarily means that your all of the voltage in the output side is fed back in the input side. If beta is less than 1, then the percentage of the output voltage is fed back. Now, if you see very carefully, the input voltage, this is the source voltage which you are giving, right. The input voltage which appears between the gate and source of Q1 is referred to as Vi. So, this is my Vi, right, input voltage, and this gives you a current here ID, right, an ID current flows through this point. This generates a voltage. How much voltage will be generated? It will be VDD minus IDRD, right, that will be V out. This V out will be fed where? Will be fed into the gate of Q2. This Q2 gate will generate a current here which is ID2, right. Suppose this is ID1, this is ID2, then ID2 will generate a voltage here which is given as VDD minus ID2 RD, right, RD2 let us suppose. This is the voltage here. Now, that voltage is your V out. So, a fraction of that depending on the value of beta is again fed back in negative. Why negative? Because if you see very carefully, this voltage is, this is positive and this is negative, and this will be reverse biasing my gate to source of Q1, right. So, my gate to source of Q1 will be reversed biased with respect to Vf, because Vf, this is positive, just like a source degeneration resistance, remember. Exactly the same happens here as well, and therefore, it tries to reverse bias this transistor Q1, right, and therefore, you have negative feedback network here. The obvious reason why generally we have two transistors is that one is a driver transistor, another is a transistor which has been driven by this Q1, and therefore, that is the voltage which you see from the outside world, right, and you are able to sustain this this formulation here. Depending on how you look into it, we will see automatically that by application of a reverse bias here, your input impedance actually rises with feedback. So, with feedback RF, if I want to find out input, so if I want to find out RIF, which is input impedance with respect to feedback, I get without feedback RI 1 plus A beta as the increase in the input impedance. In this case, you will see that this is negative feedback, primarily meaning therefore that A is less than 0, beta is also less than 0. So, when you multiply both of them, you get a positive sign, and therefore, you will get a negative feedback. From this physically, let me explain to you how I get negative feedback. So, as I discussed with you, as this Vs increases, this voltage increases, this current increases. So, this voltage drops down, which means that this current here will drop down, which means that this voltage will increase. So, with increase in Vs here, I get an increase in the voltage here, right. But this increase in voltage primarily means that my Vf will also go on increasing, and as a result it will negative feedback my Qf in a much more larger term, and that is the reason, that is the basic origin of negative feedback here. And as you can see here, therefore, that depending on the effective values of the gain of Q1 and Q2, this factor will be typically very large. You can get a very large gain here at the output of Q2, and that will be fed through R1 R2 network back as a negative feedback onto Q2. So, this is your voltage feedback network. The most, as I discussed with you, the most the convenient form is basically a voltage mixing and voltage sampling. No need to say, we have discussed this point time and again. Because of the series connection at the input and the parallel connection at the output, this topology is also known as series shunt feedback, because we refer to this mixer side as the series first and the sampler side as the shunt, and therefore, we refer this to as a series shunt mechanism, or a series shunt mechanism which we see. Now, if you look at the series shunt feedback amplifier, what we can write down is that, as we discussed just now, that we get a higher input impedance and a lower output impedance, right, and that we will just show it to you through a derivation maybe, and this derivation will remain the same for almost all the cases, the methodology by which we adopt. So, if we let me draw you the effective diagram of a series shunt feedback network and explain to you how it works out, right, and I will explain to you how this is being done. So, it is AVI. I will explain these one of them individually, then you have R here, and then this is your V0, this is the output voltage, and then you have you take a parallel combination out of it, assuming V0 is the output here, we take a factor of it given as beta times V0, and I get this factor, and then this is connected to this side, and then we get like something like this, right. So, this is your amplifier A, for feed forward amplifier A, where this is your Vi and this is your Ri, and this is your Ro or R output resistance, and this is your voltage. So, this is your feedback network, this is your beta feedback network, and this is your feed forward amplifier, and this is a voltage source Vs. So, if you see very carefully, A into Vi is nothing but the output voltage which you see in the output side of the amplifier, and that is the reason I refer to this as A times Vi, and out of V0, beta times V0 is the output voltage of the feedback network. So, this is the effective circuit diagram which is seen and can be explained to you, and let me write down therefore that with feedback I get V 0 output by V s, and that is equals to A upon 1 plus A beta, right, and that is a standard form of VC. But let me write down, let me show a derivation of input impedance with feedback. I get V s upon I I out source by current, I get V s divided by V I by R I, because I I is the input current, which is nothing but the voltage, input voltage by input current, and this can be written as resistance times V s by V I, right. So, this can be written as R I times V I plus beta times A times V I divided by V I. So, I get this to be equals to R I 1 plus beta A as the value of R I f. So, your R I f shows an increase by a factor of 1 plus beta A. So, in general, if you want to generalize it, I can write down Z of I f, which is impedance with respect to frequency, now I am writing out, is equals to Z I of s into 1 plus A s into beta times s. See, what we are assuming till now was that we are assuming that the feedback network is not loading your amplifier, neither your load which is there RL is loading your amplifier. So, just they are working on a standalone basis, right. In reality this is not true, there is always a loading, and then second thing is that it is also frequency dependent. For example, the gain of the amplifier is again a frequency dependent quantity. You must have known by this time that in the mid frequency only your gain is stabilized and gives you a constant value. At very low frequencies and high frequencies the gain starts to fall down. So, therefore, it has to be a frequency dependent quantity, and therefore, I write down to be as AS. Similarly, beta, if it is a purely passive network, it will be independent of frequency, but if it is an active network, it will be also having a frequency dependent term coming into picture, and that is the reason I write a generalized formula for any voltage amplifier in this form, in the form given here. Let me show you for ROF, which is the output impedance here. Let me do it in the next page maybe. ROF, which is the output resistance, is given as Vi by I, where I is given as Vi times AVI by RO, because you see it is minus because you are doing a negative feedback. Now, what we do is that for finding out the output impedance, we short the input, and therefore Vs equals to 0. I get Vi equals to obviously equals to minus Vf, which is equals to minus beta times V0, which is nothing but minus beta times Vi, because Vi and V0 are constant in this case. So, I get current to be equals to Vi plus A beta times Vi divided by R0. So, I get therefore ROF, right, ROF to be equals to R0 divided by 1 plus A beta, because you see we take Vi common, right, you take Vi common, and so this will be I equals to Vi 1 plus A beta divided by RO, right. So, if you take if you take this to this side and just vice versa, I will get RO by 1 plus A beta, right, is equals to Vi by I. Now, the Vi by I is nothing but ROF. So, ROF is equals to RO upon 1 plus A beta, right, and that is what you get. In general, we can write down therefore ZOF with feedback output impedance can be given as ZO of S upon 1 plus, as I discussed with you, beta times S, and this is what you get from the overall discussion, this value which is available with me. So, we have seen that the input impedance rises and the output impedance falls down. And that is the intuitive result which we have already found out, because it is a parallel, output is a parallel connection. So, output parallel connection primarily means that output impedance will fall down, right, and that is the reason you get a reduction in the output impedance. Let me show to you now an example wherein you have another example here, which is basically this is your current amplifier. Another example is basically this one, wherein you have got your amplifier here, this is your A. So, this is basically an op amp, and this gives you a feedback region, and this R1 is responsible for giving you a feedback to the amplifier, and beta therefore will be equals to R1 upon R1 plus R2, right, because they are in series with respect to each other. Similarly, if you want to make it much more simpler, you will see that it is exactly the same as this one here, right, and this is the feedback network which you see here, right. This is a common source stage, because common gate, because you are giving the source input signal to the source side of it, and so source to gate, so Vi will be between VGS, which is between these 2 points, and therefore you will automatically get a variation in the output frequency or output voltage here. Let me come to the current amplifier here now. The first was a voltage, is a current. So, input is a current, output is also a current. So, and therefore, since it is a current amplifier, we represent it by a Norton equivalent, right. So, if it is a voltage, you must be knowing from your basic network theory courses or your electrical technology courses that voltage sources or voltage related can be done very well with Thevenin, and current can be done very well with Norton equivalents. The output interest, as I discussed with you, is current, hence the feedback network should sample output current, and therefore output current will be sampled in the output side. The feedback signal should also be a current, so it may be mixed in shunt with the current source, and the most feedback topology is basically current mixing and current sampling topology, and I will see to you how it works out, because again if you have understood voltage amplifier, this is just a complementary form of voltage amplifier. This is basically the previous one was series shunt, this is basically a shunt series amplifier. So, we take series in the output side because we are trying to take out current. So, the output side you will have a series connection, and the input side you are feeding a voltage. So, you will have automatically a voltage consideration, right. As I discussed with you, you will have a lower input resistance and a higher output resistance, just the reverse of the previous cases. And please understand that when you are discussing shunt series amplifier, for example, you have to be very cautious that it is basically a current source, right. It is basically a current source which you are referring to. Now, if you remember, current source output impedance is infinitely high, right, and as a result what will happen is when the current source infinite it is relatively high, you want your output impedance to be high with feedback, because if your output impedance is high with respect to feedback, you automatically get much more stabilized current source with you, and that is the reason current series feedback or a current series helps you to achieve that phenomena. This is an example of your current series feedback network, and as you can see here I am feeding through a current source here IS, and this is my gate voltage which is fixed. Of course, this as I discussed with you, you will be taking output from the parallel side. So, the parallel is basically RF and RM are in parallel with respect to each other, and therefore, depending upon the voltage appearing across RL, part of it will be divided between RF and RM, and there will be a negative feedback to your Q1, right. As a result, this Q1 will be reversed biased with respect to each other. As I discussed with you earlier also, the voltage here will be nothing but VDD minus ID times RD, and therefore, that voltage will be switching on my Q2, and there will be current I0 flowing through this point. I0 into RL will be the voltage, that voltage will be divided between RF and RM, and a part of it will be fed into the negative feedback of Q1, and you will get a negative feedback amplifier available in this case. Let me come to the transconductance amplifier. Transconductance amplifier is that so the first one was voltage, so input was voltage, output was a voltage. I used VCCS, which is voltage controlled current source. Then we have a current controlled current source, so it is a current amplifier, second one. Now, we will have the first time where the input is basically a voltage and the output is basically a current. So, my input, so I will have a voltage controlled current source, right. So, I have a voltage controlled current source. So, VCCS, right. So, the first one was voltage controlled voltage source, the second was current controlled current source, the third one is basically voltage controlled current source. So, as I discussed with you, you will be mixing voltage and sampling currents in this topology. This is also referred to as a series because both sides, sampling and input side, you will be having both side, you will have series combinations with you, and that is the reason you will have it is also known as a series feedback topology. Provides transconductance amplifier, which means that it takes voltage as the input. Remember where transconductance term is coming is basically GM. So, it is del ID del VGS, right. So, if you look at transconductance, it is referred to as GM and referred to as del ID del VGS. So, which means that I give an input voltage, a gate to source voltage, which results in output current, right. So, voltage to current amplification is been shown in this case for all practical purposes. This is an example of a basic topology of your series network, right, because both sides are series. So, you have a sampling side as well as your mixer side, both sides are basically a series combination here, and you have a feedback network coming here, right. If you want to do analogy with respect to real circuits, well, you have an op amp here, and you do have this drives your Q2, right, and as a result you will see this is basically a PMOS, right. So, and you are giving to the negative side here Vi and a positive side is connected to the feedback network. So, when this voltage, when this current becomes larger and larger, the voltage drop across RF increases, this feedbacks in a negative sense to AI, and as a result the voltage here starts to fall, the current starts to fall here, right, and therefore this is basically an example of a negative feedback network for all practical purposes. The same example can be seen here as well, where we have replaced this op amp by this Q1 network here. So, this is basically a transconductance, because we are giving a voltage source Vs here which converts this into a current, and that converts into a voltage here which feeds this gate of Q2, and the same conceptually this remains the same. So, you have a series network here, right, and you do have a series network which comes into picture. Now, if you look at the series network, let me just write down for you the series network. If you write down series, right, you will see that I can write down in this format that you have got a current, you have voltage here, and then of course you will have a current here, and then you will have R0 here, right, this is Ri, this is Vi, and the same thing goes on this side, and then right, and then this is shorted, and then you have got beta times I0, because this will be a current, this will be a current here, this will be a no, so this will be a current, this will be a current, and then this will be going like this, and this is the voltage source Vs, right. If you take into consideration and do the same formulation as we did earlier, I get Rif to be equals to Ri, right, into 1 plus A beta. So, your input impedance also rises, and Rof is also equals to Ro into 1 plus A beta in this case. So, your input impedance as well as your output impedance both rise with respect to negative feedback in a series combination. So, whenever you can even if you do not understand the mathematics of it, whenever you have a series combination, the impedance rises obviously, and you have a parallel combination, the impedance falls. Now, when you have a both side, if you have both side shunt, then both there will be both the impedances will fall. Both sides series, both the impedances will rise. One side series, one side shunt, the series side the impedance will rise, and the shunt side the impedance will fall with respect to feedback. So, that general rule of thumb is most important for you to remember as far as feedback theory is concerned. We come to the last part of the amplifier, which is basically my trans resistance amplifier. In this case, it is just the reverse of the previous case, where my input is basically an input signal and the output is basically a voltage, right. So, I will have current mixing and voltage sampling here, and it is also referred to as a shunt because both sampling and mixture will have shunt regulation, and so as I discussed with you, it will give you a low input as well as a low output resistance, because it is a shunt feedback resistor. You see that I am taking a shunt here, I am taking a shunt here, and therefore, this is my RS source resistance, load resistance in the feedback network. And one of the best examples is basically your operational amplifier design, wherein you will have RF here, which is basically, so you take a shunt here because you are taking parallel from here, you are taking parallel output from here, and therefore, you are sampling it in parallel and you are mixing it in parallel in this case. So, basically this is a shunt network. Here in this case you get Rif to be equals to Ri upon 1 plus A beta, and therefore, there is a drop, and Rof is also equals to Ro upon 1 plus A beta. So, in both the cases Ri as well as Rf, your output impedance with feedback actually falls down drastically, and therefore, there is a decrease in the value of your shunt resistances in this case. So, one thing you should always remember is that in presence of shunt the impedances fall down, series both the impedances rise up, shunt series and series shunt, series will rise up, shunt will fall down, and in all the 4 cases your gain will always drop down if you have a negative feedback. So, this is a common thread across all the amplifier which you see. You will ask me why this is important. Well, this is important because now you have an amplifier, because you remember your maximum power transfer theorem from your basic network theory courses, wherein you need to make your output impedance of the driver equal to that of the load, input impedance of the load, for a maximum power to be transferred. So, when you have these type of amplifiers sitting in between your load and your source, then you can change your output impedance in such a manner that it becomes almost equals to the input impedance of the external load, and therefore, the maximum power will be transferred from the chip or on the circuit to the load, external load, right. So, that is one of the major advantages of having feedback, that you can control the impedances in the input and output form by simply choosing the type of configurations which you want to do, right, and that is the important part which you will see here. This is another example. I will not talk about BJT, maybe MOS device you can see here. This is basically shunt again. So, you see here I am giving a VG, I am giving IS, as in the previous case. This RF is basically in series to this one. As a result, this voltage across this will be feeding back this in reverse direction, and you automatically get a negative feedback concept in this case, right, for a shunt case. Right. So, let me recapitulate what we did. What we did was that two important assumptions we have taken, that there is no loading of the amplifier or the feedback network. In reality, not true, you will always have a loading, howsoever the loading is low is still there. The second thing is we have taken them to be almost independent of frequencies, but therefore, our definition of understanding here stands very well within the domain of mid frequency band, where your gain is almost stable with respect to frequency, right, and at higher and lower frequencies, if you remember, the gain starts to fall down, and therefore, there these things might not be very valid in a sense. We have also assumed that the feedback network does not load your basic amplifier. Well, that is very important, that it does not load, and this gives me a proper feedback. Advantage of such a network, studying such topologies, is that you have a methodology with you by which you can vary the impedance levels at input and output of an amplifier, and therefore, you can have a good driver available with you while driving an input signal to an external load, right. So, with this, let me thank you for your patient hearing, and we will talk about other topologies in the next module. Thank you very much.